Now the next formula that we'll see involves doubling time. That is the amount of time it would take for an investment to double. And there are doubling time formulas for any version of a compound interest formula. But we're just going to look at the continuously compounding interest example. So we know that P e to the RT is equal to the amount that you'll have. So your principal invested at R for T time will give you A. Now if we want to double our amount, that is double your initial amount, that means that we want the final amount to be 2 times the principal. Okay, so putting that all together, we want to find T. We want to find T when the final amount is equal to 2p. In other words, when 2p is equal to p times e to the RT, the final amount. So this formula is actually pretty easy to solve. We're going to hold p and r constant and just see what time is involved. Okay, so we want to solve for t in this case. We can do that by first dividing by p. So if we divide both sides by p, we can cancel a p and just be left with 2 on the left and e to the RT. Okay, now we could ln both sides in order to cancel out the e. Alright, so lnning 2 will give you a number, the natural log of 2, whatever that is. And lnning e to a power, this is one of our properties of logarithms, will effectively annihilate, right? The natural log function and e to the power function are inverses. So on the right-hand side, we'll just end up with r times t. So the ln of 2 is equal to r times t. Now if we divide both sides by r, we have t, the doubling time. And finally, that means that t, the amount of time it takes for an investment to double, only really depends on the interest rate. So the natural log of 2 divided by r. And that kind of makes sense. This is a rational relationship between t and r, a variation, an inverse variation, if you will. As r gets larger, if r is very large, the amount of time will be small. The natural log of 2 is constant, so we're dividing by a large number and we'll get a small number. If the interest rate is very small, it will take longer for our investment to double, and that intuitively makes sense, right? So our formula for doubling time is going to be very useful in the next exercise, where we have Hannah back again. This time she has $20,000, and she wants to see how long it will take to double in value at 5% compounded continuously. Now, we mentioned briefly that we're only going to look at the continuously compounding interest version of things. That means that we can count on that formula. If the interest were compounded weekly or semi-annually, this formula would not apply. Okay, so just to highlight this, this is only the formula when we talk about compound interest, or continuously compounded interest. Okay, so we want her investment to double. What do we need? Well, we're interested in the time, t. we know that's equal to the natural log of 2 divided by the interest rate. So we don't actually care about the $20,000 she's investing. If she were investing $20,000, it would double in the same time that a $50,000 investment would double. So we can just plug in R. ln of 2 divided by R, and again, always use that decimal version, 0.05. We'll throw that in the calculator. The natural log of 2, closing parentheses, divided by 0.05 is about 14 years. All right. Now, time, in this case, will always be measured in years. If you're compounding continuously, time is always going to be years. So we don't have to worry about the units, but it is a good idea to include them. Now, does that time frame make sense? Well, you could set this up in a different way. You could say, when will P to the RT be equal to 40,000? In other words, when will the amount that she invests at this rate be equal to 40,000? And then solve that algebraically using similar techniques to the original derivation. That will hopefully result in the same number. This is a good way to check. Failing that, you could go back and plug 14 years into PERT and see if you end up with the $40,000 that we're hoping for.